Okay, chapter 4, we're dealing with actually force system resultants, which is down here. Let's try that again. Force system resultants. That's the title of our chapter right now. That's dealing with, we've dealt with forces in the first exam in chapters 1 through 3, and we sum them up in all directions, so we came up with a resultant force. So moving forward here in chapter 4 and 5, we're going to talk about, okay, once we have these forces resolved into a net force or resultant force, how does it affect the body? How does it interact with the body or object under study? So a quick step back here to some physics 1 stuff. When we had a force go through the center of an object, and I'll just call that a net force, and it went through the center of that object, the object was displaced but there is no rotation, meaning the object just translated. The object just translated. However, when we had a force, I'll make the object just a little bigger, instead of pushing through the center of mass, when it was at a distance to the center of mass, we found that the object rotated. Force acting at a distance from the center of mass. And it was referred to in physics 1 as torque. We're going to be dealing with this situation, but we're talking about the tendency to rotate because we're still in statics, so we're not going to allow things to rotate, but the object is going to feel or want to rotate, but since it's in statics, it's sort of held in place. It's like someone trying to twist your arm, but your arm doesn't twist because you're holding it so tight, but you feel that tendency of it wanting to twist. You can feel that there's something going on rotationally. Now, physics 1 uses the term torque because typically it's talking about the force twisting or torquing the object. In statics, we tend to have the point of view of from the object's point of view. So instead of torquing something, we're being torqued, but in statics or engineering, we refer to that as moment. So it could be known as torque, but we refer to it as moment. So we're going to look in this chapter and some following chapters of force systems or resultant forces or net forces or any force creating a moment of a force or just a moment. We use capital M because it is a vector. We'll put the arrow on top. It can happen in 2D and 3D. And it's a measure of the tendency of a force to cause a body to rotate about a point or axis. All right, it's force about a point or an axis, often called moment of force. And if you go back to the beginning of class, you may have remembered me saying you have to learn 2 things this semester. Some forces, so there's no translation, and some moments equal to 0, which means there's no rotation. So we've dealt with the first one already. Now we're going to deal with this second one of summing the moments to 0. First, we're going to learn how to calculate or determine the moment or net moment or resultant moment, just like we did with forces. And then we'll apply the equations of equilibrium so that the moment equals 0, so that we remain in static mode. All right, so how do we calculate it? When we're in 2D, we calculate with a force times distance. We typically want that force to either be perpendicular to the distance, or we want the distance to be perpendicular to the force. And let me draw up here. I'm going to put a force right here. We're not going to worry about being net or resultant. That's obvious one in a y direction. We have a distance from here to the force. There's the origin. We'll call it D, and D is in the x direction. And that force pushing at that distance, if this is held stationary, is having a tendency to want to rotate that arm about O. Now, is it trying to rotate the entire sort of side T structure that I've made there? Yeah, essentially. But the idea is it's rotating it, and that would be about our Z axes. If those are in the XY plane, if the F and the D are in the XY plane, which they are, then that would be a rotation about the Z axes. And that would be our two-dimensional. And I could put forces all over the place and just look at rotation, or I could have picked a different point. We're just picking the origin at now. We'll find the moment about essentially the origin. So the plane that the force and the distance are in, the moment will be set up in a plane perpendicular to that plane. Now, if we're in 3D, let's have that force. And here we have y, there's x, and then z is vertical. If I have this force here, and that would be in the negative x direction, and that d is that distance there along that arm also, it would be trying to create a moment about the z axis. And that would be the moment of O, and that would be in the z direction. Okay. Now, if that's set up and they're all nice in their x, y, and z's, it's pretty easy that we can use moment is force times distance. However, if it's truly in 3D where the distance and the force are vectors in some random plane, we have to find it from R cross F. Again, if it's easily, we can use the two-dimensional version, but we use R cross F. And lastly, just to modify this in 2 dimensions here, excuse me, if we don't have the perpendicular, we can use the sine of the angle between to find the perpendicular of either the force or distance, and then find the moment that way. And while we're here, let's just add units. Since it's force times distance, it's going to be Newton meters or pounds foot or foot pounds. If you work on cars and use a torque wrench, they usually have units of foot pounds. Will be in Newton meters, capital N, small n. All right, so we're looking at the tendency of this force or forces to create rotation about a point or an axis. And even if there's no movement, if there's no rotation, a moment is still produced about that point or axis. Okay, in this one, it's really about a point. And here we're finding it about an axis when we go to 3D. And the general case for the equations is just force times distance. All right, any questions up to that point? Okay, let's go to another page here. I'm going to do a little bit more lecture before we start cranking out some So looking at this equation, the general equation for a moment, the moment will equal 0 when either the force equals 0, meaning there's no force present, or the distance equals 0. For the distance equals 0, the force is acting directly through the point or the axis of interest. The force is pushing through the axis or point of interest. Here's our door. Here's some hinges. We'll assume the door is open. If I push through here, I'll call it F1. We'll call this H because it's the hinges. The moment said about the hinges is going to be force 1 times distance. We'll call that distance 1. And whatever that numeric value would come up would be the moment. So that would be some number of Newton meters, and we would put that right there. In 2 dimensions, we use a curl, sort of that arrow curled, to represent the direction of the moment. Okay? In 2 dimensions, we do that. That is considered positive. That is considered a positive direction. And we're going to use our right-hand rule for the direction of the vector. So if you would put an answer up there and leave it as 35 Newton meters, I would take that as counterclockwise. If it was the other direction, which is clockwise, meaning that door was open, you're pulling that door, you weren't pushing it open, right? Because clockwise would be this, or counterclockwise. If you were actually pulling the door open and told me 35, I still assume that's counterclockwise. So you want to put a arrow there. It's best to put the arrow or the curl instead of plus or minus, because that makes it really obvious. Now, getting back to this point up here, that if the distance is 0, if I would push with a force 2 that has 0 distance, I'm going to say moment of h due to 2 equals force 2 times distance of 0. We get 0 moment. I can push and pull on those hinges all I want. I will not get the door to rotate or spin because I'm pushing or pulling through the rotation point or rotation axis. All right, that's sort of looking at it in 2D. What if we're looking at it in 3D? Let me bring back this little drawing I had there. Let's see if I can do this without too much trouble. There we go. I'll draw. Nope. That's cool, but I don't want to do that. There's our little object again, and we can X, Y, Z. We're going to have the force there. I'll call it force 1. There's distance 1 from there to there. That's going to create, as we saw, a moment that spins about this axis. There's the moment about O. And we'd say the moment about O is R cross F, which in our case is the distance, 1 cross F1. And when we get that answer, it will be in I, J, and K. But it turns out if those are in I and J, this will only be in K. But what we do is we draw it like this. That is the plus direction. We use a vector arrow with a curl about it to show the axes. Something like this. And we're going to use the right-hand rule for this. Right-hand rule, fingers. Direction of R or D. And then we curl in direction of F because we are R crossing into F gives us the moment. And then the thumb direction of the moment. So in this case, we take D, we're going to sort of point it over this way. There's our fingers pointing that way, all 6 of them. Don't forget my wristband. We're going to curl them in the direction of F. So that is R. We curl in the direction of F, and the thumb gives us the moment. Now, we don't need that right-hand rule for the mathematical calculation of it, but it allows us to get a good sense of the direction of the moment. So when we get our answer, we can get a check on that. So that's looking at 2D. This is 3D. Obviously, if we just push on this straight through here with F2, we get the moment about O due to F2 would be R2 times F2. That would be 0 crossed with a vector equals 0 because we're pushing. It's like pushing on these hinges on a three-dimensional door. And lastly, I'm going to just put in here so I don't have to have a separate slide just for this. The total or resultant moment will just equal all the individual moments, which is really just adding up all the force times distances in 2D, or adding up all the R cross Fs in 3D. So if we have more than one force, we find the moment of each of those forces, and then we add them together. Algebraically, if we're in 2D, and if we're in 3D, we add those with I, J, and K in 3D. All right, any questions before we start kicking some problems here? All right, real simple problem here before we get to the other ones I have from the book. We'll have a simply supported beam here. Simply supported beam, 10 newtons down here in the middle. Let's make this 2 meters and 2 meters. So the whole thing is 4 meters long, and then we have a second force, 20 newtons at 30 degrees. We'll refer to that as the origin. So we're going to find the moment of each force individually, and then we'll find the MR, resultant moment at O. We'd call that MRO. 2D problem, algebraic, pretty straightforward and easy to do. All right, let's find the moment of each. So I'm going to find the moment of the 10 about O. Again, that's force times distance. We're looking for perpendicular, one or the other. That's already 10 newtons. That's at a 2 meter distance. It's already perpendicular. So that becomes 20 Newton meters. And I put the arrow that way to show that it is clockwise. Again, we typically think of, or we view counterclockwise as positive. I'm not sure exactly why that is. It's just the way that I was taught also. I think it's that if we have this beam, let's say it's a deck, if it fell, if it rotated clockwise and failed downwards, like rotated about the hinge and failed downwards, that would be bad. And so we take that as negative. That's kind of how the way I think of it. So if the moment is positive, meaning it's counterclockwise, that means we're holding this thing up. All right, so that's the moment of the 10. What about the moment of the 20 about O? Again, force times distance. That force, however, is not perpendicular, so what we have to do because of the angle, we have to put it into X and Y components. Now the moment is going to be due to both of those. So it's going to be due to the force in the Y direction at the distance X plus the force in the X direction component times the distance Y. So here's the force in the Y, here's the force in the X. Distance would be here. There's the distance in the X. So force in the Y is going to be 20 sine of 30 because it's the side opposite, and that's a distance of 4 meters. That is in the plus direction, so I'm going to leave it as plus. We always want to show direction there. And the force in the X direction is going to be 20 cosine of 30. And that distance is 0. Now let's look at this real briefly here. I think that makes sense at 0 because that force basically pulls through point 0. Now, if I had a case, and I'll just exaggerate the thickness of this beam. If I had the case where point 0 is actually located right there along the center line, and that force was up here, so it pulled at some very slim distance it would create a moment, if that's our x, it would create a moment about that because of that little offset of the force from the rotation point. However, if the force pulls straight through, like in this orange one, there would be 0 moment set up. So how are you going to know that on an exam? Which one do you use? If you're given the dimensions of this beam, then you can look at the offset of that force and whether it's going to create a little micro moment there. Since we are not given any information about the thickness of the beam in this problem, we would ignore that moment there. It may be creating a little, because it doesn't, we don't know if the force is acting right here or if it's halfway in the middle or if it's down in the bottom, but it obviously isn't a concern for the designer because they didn't tell us anything about that. So if we're not given any dimensions for the thickness, just ignore it. All right, if we finish this problem out, 20 sine of 13, what's that? Sine is half. 40 Newton meters. And that's also that direction. Part B, resultant moment. Again, positive counterclockwise is adding up all the individual moments. We're going to have a 20, but we have to make that negative. Why do we have to make that negative? Because it was negative up here when we calculated it. Plus the 40 equals 20 Newton meters positive. Now again, this one is this way and this one is a positive this way. I like to put the arrows underneath because it reminds me direction, because if it's this way, it has to have a negative. If it's counterclockwise, clockwise, it should have a negative. Counterclockwise should be a positive, which is there's our net moment. So it's saying the result of those forces gives a moment of 20 Newton meters clockwise. Clockwise assumed when it's positive, unless you tell me otherwise. Now you may ask, hey, why can't we do what we did in the last chapter and sum up all the forces to get an F net and then find the moment from the F net or F resultant distance? Great question. We can in certain situations. In this situation, for this problem, we cannot, because, why can we not? Because these forces all have different distances. So adding up the forces will give us a resultant force, but it doesn't associate a distance with each individual one. I just can't add these up and get a 20, a 20 up or something like that, or a 10 up, and then multiply by some distance. However, if the problem, let me just draw it, I'll put it down here. If the problem had a bunch of forces that act all at the same point, if they're acting all at the same point, then yes, I could add them up first and then take the resultant force times that distance. So there are situations we can do that, but only if they act to the same point. Okay, questions on that problem? I need to introduce something real quick before we go into Come on. Line of action of a force. If I have a force pulling like that, we'll give it a vector designation. We typically draw this to sort of to scale if we can, if there's other forces and we need to sort of draw to scale to help us, but we don't have to. But that force acts all along that 3D line, and that's the line of action of the force. Typically we would probably just draw it with dashed lines to show that maybe it goes here, maybe it starts down at this 3D point, and maybe it pulls to a point on the wall. We don't know, but that's the line of action of the force, meaning that force extends infinitely in either direction. For example, if I go back to my beam and I have my force there, that's at 30 degrees, and we'll call that 20 newtons again. Again, that's 4 meters. The line of action of that force extends in either direction infinitely. So why does that matter? Well, our first solution was we did moment equals force times distance, and we used sine and cosine to find the components. And then we solved it. The other way is to look at this extension here, and instead of getting the perpendicular using sine and cosine, if we just extend that line until we find the perpendicular distance, and that becomes the force perpendicular. If we extend that line, if that's 4 meters, there's that. This should be, if that's a 30, that makes that 30. That makes that 60. We can find this angle from 4 cosine of 60 degrees. So we could, instead of sine and cosining the force, we can sine and cosine the distance to find that, and then it would be the moment about O would be 20 times 4 cosine of 60. Cosine of 60 is half, so that's 2. That ends up being 40 Newton meters that way. And that's the same answer we got before. So the line of action is a way we can extend that line. Sometimes it's helpful. I still think sine and cosining the force is the easier method, at least for me. That's the way I've sort of looked at it, instead of sine or cosining the distance. But if that triangle there that we drew with the red dashes ends up being a 3, 4, 5 or something like that, or 5, 12, 13, so we could use ratios, then maybe that's an option to consider. All right, let's hammer some problems here. All right, we already did that one. Let's move that up there. All right, problem right out of the book. Moment about a point. We're asked to find the moment about A. Okay, A sits right there at that point there. Now, if you'll look, I talked about earlier. Let's try that again. Here they're giving us the thickness or the offset of that force from the top of the beam. That tells me I have to include that small distance when I'm finding the moments about A. All right, I have to be aware of that. So let's do this in 2 steps though. Before we find that, let's find the moment of each force about A. That would be the steps you would get anyway. You'd have to find the moment of all three of them, and then you add them together to get the resultant moment about A. So let's not jump to the end right off the bat. Let's do the individual steps, all right? First one in statics is always going to be, our first step is always going to be a free body diagram. Now these drawings right here are pretty much free body diagrams as they are. The only thing I would change here is I have to find the X and Y there, and I have to find the X and Y of that force. I'm not worried about the reaction at A and what's happening at A other than the moment, and we're going to call positive counterclockwise. So first step would be free body diagram, and then we're going to find the moment of each one. We are in 2D, so we should be able to use force times distance. All right, let's find the moment. Do the first one. So moment 1 will equal, moment 1 about A will equal F1 times D1. F1 is 375 pounds. F1 is 375 pounds. What happened there? Our distance is going to be is that 8 feet? And since we're taking counterclockwise is positive, that will be a negative answer because it's trying to rotate it down. And if we take 375 times 8, we get minus 3,000 pounds foot. We could say foot pounds. Nobody's going to yell at us. So we'd either say minus 3,000 or we'd write this as 3,000 foot pounds, and then we put that. That would be the same answer there because it's trying to rotate it down about point A. All right, what about the moment of 2 about A? So that's going to be force 2 times distance 2. Now we have two forces. We have a force there that's at an angle, so we have to sort of find the components first. So that'll be F2 in the x direction times distance y plus F2 in the y directions times distance x. Since point A sits right on the top of the beam and that force is pushing on the top of the beam, there's going to be no distance y. So we're only worried about the vertical component and the horizontal distance. So that would be 500. Even if I just put it in here knowing it, that's going to be the 3/5 times the distance of 0. F2y is going to be 500. What is that, 4/5? Using a little triangle. And that's a distance of 14. And if I go through that mess, it's 100, 400. I think that's 400 times 14. $5,600 foot-pounds. And that's also negative, so I draw the arrow that way. All right, let's finish up. Moment of 3, force 3 about A. Again, counterclockwise, still positive. We have the two components. Here's the Fy component. Here's the Fx. So I'll need the Fx of 3 component times distance of y plus the Fy of 3 times distance x. The x component will be 160 sine of 30 degrees times the distance. Now there we are. There's that little offset distance. It's 0.5. This one is trying to rotate it up. So that would be a positive. And the force Y is going to be 160 cosine of 30 times the distance x of, I think that's 1419 feet. And since that's trying to pull it down, which would be negative, we want to make sure that we have the negative right there. Right? Negative there means we have to put it there since we call positive counterclockwise. I think this comes out to be 40, a plus 40. 160 times 30 cosine is 138 and change times 19. 2632.7 minus that little 40 gives me a roughly 2593 minus, which is 2593 that way, foot-pounds. And then find the resultant moment at A due to those three different forces. We would add them all up. So it's the minus 2593 minus 5600 minus 3000. I don't think I did that right. Hang on. 2593 plus the 5600 plus the 3000, 11,193. Foot-pounds. All right, real quick sort of gut check. Does this make any sense at all, this answer? Well, numerically I can't without checking my math. But since if we look at it this way and say, let me get a different color here. All right. This force here is trying to rotate this way. This force here, if we extend that line of action, is also trying to rotate this way. This one's pulling it down. That's also that way. So all three of these are trying to rotate it rotate it clockwise, which means a negative answer. So that makes sense there. And since all three are coming together, that kind of makes sense. All right, all of them became negatives. All of them were negatives. So that makes sense. So I have a pretty good feeling, at least my process put me in the right direction. Numerically, again, it may not be the correct answer, but I feel like my solution went there. And again, for math problems, if I can find them, it's -1. Unless you have multiple math problems all over, then it's a few more points, but I'm looking for the process. Okay, questions on that problem? Nice, simple 2D problem. Actually, the second 2D problem. All right, let's move to a 3D problem. We're given a force. It acts at the end of this C beam, the C shape. It's not an I beam because it's not an I shape. It's not an H or a box. Sort of has this C. You see this sometimes in new construction for rooms. They use sort of these aluminum 2x4s instead of wood 2x4s. And they sort of have this shape. And usually we have a shape like that so something doesn't bend. We don't have to enclose it to make it a complete box. All right, so we are in 3D. When we find a moment in 3D, it's going to be R cross F. This is the cross product. This is something that should have been covered in your Calc 3 class, which you should be in or have already taken. And we write that out as IJK, RX, RY, RZ, FX, FY, FZ. So 3 by 3 through by determinant, matrices, whatever you've been told it is, however you want to call it. This tells us the axis. We'll get to that later. This is obviously the position vector. That's the components IJK of the position vector, and that's our force vector. Now, the answer of that will come out to have an mx in the I, an my in the j, and an mz in the k, and then units. Shorthand, like that. It is not a scalar product. A scalar product will give us just a scalar answer, a number, numeric, a magnitude. This cross product gives us this. All right, so we want to find the moment of the force about A. We're given the force, or I'm going to give you the force, is a 600I, 300J, and a minus 600K. And that's Newton, so that's given, along with the drawing. Now, is the direction of that force drawn there correct? I would sort of take it as that, but we can't always assume. But it does have a line of action that continues in both directions. So what we're trying to find is the moment at A, and A is drawn right here on the top. We're to assume actually, let's find about O. Let's start out by finding about O, just to simplify things because I don't have everything on this drawing. So the moment about O, it's going to have a position vector that goes from O to the force. Now this position vector can go from the point of interest, here it's O, to any point on the force, meaning I could use the position vector goes from here to here. I could use a position vector goes from here to here. I could use position vector goes here to here, or here to here. There's essentially an infinite number of position vectors I could use. However, there's one or maybe two at most that are a lot easier. I'm going to take away these. That are a lot easier because of what you're given in the problem. We are told what point B is. From the drawing, at least, we know what it is. It's going to be 0.2, 1.2, and 0.4. So this position vector we want to use would be easiest to take it from the point of interest to a point on the line of action. So we're going to want to use OB. We want to go from the origin, which is pretty easy coordinate-wise, to B. That means when we build OB, we're going to take the we're going to take the B minus the O coordinates to build that. And since we're R crossing into F, we have to point to the F. I don't take B to O. That gives me a totally opposite moment. It's R crossing into F, so I point through R. I'm going to point this way with my fingers. I'm going to bend them in the direction of F. which looks like I'm going to have a moment that is spinning downwards in the negative z direction, right? From right-hand rule. And if you're a righty, make sure you put down your pencil before you do this. I'm a lefty, so it's easy to do right-hand rule. Righties tend to forget to put down their pencil, and they do a left-hand rule without knowing it. So through the right-hand rule, R crossing into F should have your thumb, that's your thumb, pointing downwards. So we're expecting a moment, or the moment arm, the result moment sort of be down that way. So when we get our answer down here, I'm going to expect at least a negative z. Okay? So let's continue with this solution here. Let's build our 3x3. Again, across the top, we're not going to worry about that at all, or right now. That just gives us our IJK. We'll use that later when we want to know what's the moment about a specific axis. Then we will adjust those. Position vector, we have to build a position vector. Let's go back up here. B coordinates, that's going to be a 0.2, a 1.2, and a 0.4. So here we have 0.2, 1.2, and a 0.4. And then the force, we're already given the force, so I can just drop that right in there. 600, 300 minus 600. All right, that's the setup. That's 90% of the problem right there. The rest is solving that. I don't have the answer here because I sort of just pulled this picture and I'm doing this on the fly. But the I component will be 0.2 times 300. I'm sorry, 1.2 times, hang on. Haven't had my morning Mountain Dew yet. The I component will be 1.2 times minus 600. Minus the J, it's always minus the J. It'll be 0.2 times minus 600. Hang on, I'm missing a lot of stuff here. All right, let me just start right over. My first day off of Mountain Dew, one cold turkey. I component, here we go. 1.2 times minus 600 minus 0.4 times 300 minus the J component, which will be 0.2 times minus 600 minus 0.4 times 600, and then plus the Z component, or the K component, sorry, is going to be 0.2 times 300 minus 1.2 times 600. And if we go all through that mess, we should get a moment in the X, moment in the Y, moment in the Z. And we put units on there, and there's the answer. All right, I'll leave that math to you. I don't want to waste too much time on that. All right, any quick questions on that problem? I'm going to make a comment or two about that. So I got my answer. I want to check something. This value right here tells me how it would rotate about the x-axis, and that would be the plus direction. This one would tell me how I'm going to rotate about the y-axis, and this would tell me about the z-axis. So when I get my answer, I should be able to say, okay, well, about the x-axis, it looked like this thing was trying to push down that way. That's a negative. That should correspond to this value here. Same thing in y. How's it spinning about y? Is it trying to rotate that? And it looks like it's trying to tilt this thing over into y. I would expect that one to be a positive number. And then z, sort of it's pushing down that way. It's kind of this. Maybe that's a negative. At least I can use those to get a gauge or a guesstimate on the answer if it made sense. The other thing, if I wanted to find a moment's magnitude, just like Pythagorean's theorem, I take mx squared, mi squared, and mz squared, find the square root, that gives me the magnitude. If I wanted to find the direction cosines, you're so happy to hear that you can still do that. I take inverse cosine of the x component over the magnitude. And we're right back to doing what we did with the resultant forces on the first chapter, finding the magnitude and finding the direction cosines. We can do the exact same thing with the moment vector. Exact same things with moment vector. All right, questions on that one? All right, let's crank through some more problems here. Moment about a point or a specified line. Moment about a point or a specified line. No change here. We're in 3 dimensions, but since everything is sort of lined up, X, Y, and Z, maybe we can sort of fake it with some 2D stuff. Let's see what we can do here. So let's start out by finding, well, we're given what we're given. Let's find a moment about point B, and then we're going to go back and find a moment about the Y axis. Okay, moment about B, B is up here, right at that corner. Now, I said earlier, maybe we can fake this with 2D. I'm not a big fan of faking a 3-dimensional problem as a 2D problem. I know there are students that will do that. They will hold on to sine and cosine to their last moment, and I get it because it should be easier. But in 3 dimensions, doing sine and cosine to get your solution, it's okay to deal with the force. Like on this force, we have to deal with these angles. But to get your final solution by using sine and cosine, I think you're setting yourself up for trouble. So force yourself to understand this R cross F, this 3-dimensional dealing with a force and a distance to get a moment. All right, let's find the force vector, meaning we're going to put this force into vector form. So again, the force is going to be F times U, which is F times, if we have to build it, R over R. Here we can sort of do it with the cosines. So the I direction is going to be 80. Cosine of 30. Okay, that brings it up to this plane right here, that line. And then we have to sine 40 to bring it over. So that's up. And that brings it over to the X. And that'll be the I direction. Cosine 30 again brings it up into this XY plane right along that component right there in orange, and then we push it over to find out actually that component. That's the force in the X. Force in the Y is going to be right here. That's going to be plus 80 cosine of 30, still bring it up. Cosine of 40 brings it over to the Y, and that'll be our J direction. And the z is actually negative because we're looking for this component right here. It's negative, so negative 80 sine of 30 degrees, because we're really just looking at that little triangle and finding that piece there. That's in the K. All right, if we go ahead and clean it up, I've already done this problem before. I get basically a 44.5, a 53.1, and a minus 40. That's our 80 vector. Come on. Come on. Silly bird. There we go. What about position vector? Well, position vector, since moment is R crossing into F, R crossing into F, we want to go from R to the force. So from the point of interest to a line of action of the force. Now, line of action of the force goes this way and this way infinitely. The only point we really are given is this right down here. So we're probably going to use, or would want to use, position vector from B to C. B to C. So let's write down those coordinates. B is 0. I'll put it into meters, 0.4, instead of dealing with 400 meters. 0, 0. And point C is going to be, what's that, 250 plus 3, it's 5.5. I'm sorry, 0.55. Try it again. 0.55. It is 0.4 over, and it's down 0.2. So to build that position vector, I'm going to take the C coordinate minus the B coordinate. Sort of try to do that in my head. I get 0.55, 0, and minus 0.2. And again, we can walk that. If we get that, we're not sure if that's right, we walk it. To go from B to C, we go plus 0.5. In the X, there's 0.3. There's another 0.25, right? Here and here. We do nothing in the Y, and then we have to go down 0.2. There's my down 0.2. That gets me to that thing. That gets me to that point. That makes sense. I'm happy with that number. So we're going to build this R cross F, I, J, and K. Across here, we'll have 0.55, 0, minus 0.2. The force vector goes in last. That's 44.5, 53.1, minus 40. And if we go through all that mess, we get like a 10.6, 13.1, and 29.2 Newton meters. All right, questions on that problem? All right, for part B, we want to find it about the y-axis. Let's do that down here. When I want to have a moment about a line or axis, and this one we're just going to do about an axis here. We'll do the y-axis. I'm going to modify this line right here. The y-axis corresponds to 0, 1, 0. 0 in the I, 1 in the J, 0 in the K. That's essentially the unit vector for that. So if I wanted to find a moment about this axis, right here it is, I'm basically trying to find out how much spin or moment is set up about that axis, plus or minus. So if I put 0, 1, and 0 in here, you should see that the J component, the I component will go away because there's a 0. The Z component goes away. And the only thing I'm left with is going to be the Y component. So if I want to find the moment about the Y axis, it's going to be 13.1 Newton meters. And since it's positive, that's the direction right there. I don't have to do any more math. I can just pull it from that answer. Now, I could certainly go ahead and recalculate that with 0, 1, 0, but I'm going to get that. I'm just going to get that component. And what that tells me is that that moment of due to the force of 80 newtons at location C is causing a rotation about the y-axis in the positive direction. And we use the right-hand rule, which is point thumb in the direction, and we spin. There's the y-axis. We spin to give a positive direction with the right-hand rule by curling our fingers, thumb in the direction of the axis. Curl our finger will be positive. So this is trying to rotate it this way. Looking at this connection right here, righty-tighty is clockwise, lefty-loosey is counterclockwise. So this moment about here that's this direction is actually lefty-loosey, has the potential to unscrew or loosen that connection right there, that pipe connection, if it's a screw-in. Right, with a screwdriver, right? You turn it to the right, clockwise, it tightens. Left, it looses. So since this has a positive moment, meaning it's going this way in a positive direction from the right-hand rule, this would have a tendency to try to loosen that pipe connection up. And that's sort of pulling into reality. That's why, who cares what the moment is? Well, we do care if that force is going to cause that thing to unscrew and possibly fail or start to leak, then yes, it becomes a problem. So maybe it needs, if this was some pipe assembly in the basement or something, we would have to have something that comes up here and connects with the ceiling, some rod or wire that holds this thing up so it doesn't rotate down. Who knows? But again, that's for the designer. We're trying to just look through this to find out what the loads are. Okay, questions on that problem? I think that's a really good problem. In my notes, I'm going to put a star there so make sure I study that for the next test. Hint, hint, say no more. All right, let's go a little further, do another problem. Let's look at this car here, the car hood. We have a force acting. We're told that the force, a better color here, force is 24 pounds. And it's basically going from A to B along that strut. So when you open your car hood, hopefully you've learned to do this and check your oil, or to add oil, or to add water for wiper fluid, or if you have to jump start, you lift up the hood, which pivots along the y-axis right there where it's connected to the car, and then there's a strut or a rod that you lift up. It pivots at A, you lift it up and put it in B, and it holds the lid up. Why? Because gravity is trying to moment or rotate the hood down, and we have the force that counters that moment by acting at a distance from the rotation point. So it's really moment of the hood down counteracted by the moment created by the force up. As long as the rod can support it, there's no movement. It doesn't land on your head. All right. So we want to know what's happening along this hinge here. The hinge is along the y-axis. And we want to find out the moment of the force about the hinge. Since it's pushing up, we'd expect the moment to be that way, to be holding it up, which is a negative y. And we have the force. We are in 3D, so we are going to want to use the moment about the y is going to be r cross f of the 24. And that is three-dimensional. So we're going to need a position vector. Okay. Let's build the force first. The force is going to be the magnitude times a unit vector, which is the same as the magnitude times position vector over its magnitude. So Fu becomes F R over R. That's going to be 24 times, let's see if we can sort of do this in our head, position vector. What position vector do we want to use? Well, again, it has to go from the line, the line of interest, the rotation line of interest, the rotation point of interest, the rotation axis, to a point on the line of action of the force. So I could use a position vector that goes from the origin to B. Or I could use it from the origin to A. I could use a point out here and find another random point on the force and use that one, but I want to take advantage of the coordinates I'm already given. Okay. Now B has a coordinate up there that is, what's that coordinate of B going to be? Looks like 2. 2 out, 2 over, 4 up. What about coordinate A? Coordinate A is 4 over, 0 over, 0 up. We can use either of those to go from the y-axis to the point. However, when I see a lot of zeros in a coordinate, that means my position vector is going to be a lot cleaner. Okay? Cleaner in that there's less math to do because I'm either subtracting 0 or subtracting a number from 0. So I'm going to use a position vector from the origin today. Now, we're told that we want to find out about the line or about the y-axis, right? So I need the position vector actually to go from the y-axis to the point on the line of action of the force. So I can use any point along the y-axis, but the origin is on the y-axis, so I'm going to use that. So when I build that position vector, 0 to A, I'm going to get 4, 0, 0. Okay? That gives me a line from the origin to point A for me to cross it. Now, we're trying to build the force vector. So is that the position vector I need? No. In here, we're going to need a position vector that goes from A to B because that's what the force is acting through. All right, I need the position vector goes from A to B. O to A is going to be nice when I get to my force vector. So just want to see the difference there. So on top here, from A to B, we're going to take the B coordinate minus the A coordinate. That gives us a -2, gives us a 2, gives us a 4. So that's -2i plus 2j plus 4k on top. On the bottom, we take the magnitude, so it's a square of each of those, -2 squared plus 2 squared plus 4 squared. I did this problem earlier. If you go through this, you get -9.8, 9.8, and 19.6. And we're in pounds, so it's that. That is the force vector put in force, 24 pounds put into vector, Cartesian vector notation. Now, since I have the force, and I have position vector that connects the force to the line, I can build my determinant here. So that'll be 4, 0, 0. This is -9.8, 9.8, 19.6. I have to look at what I'm going to put up top here. Now, if I put 1, 1, 1, then I'm finding all the axes. But if I put 0, 1, 0, I'm finding what the moment is about the y-axis. If I want to know the x-axis, I put 1 there. Z-axis, I put 1 there. So if I go through that, I get -78.4 pounds. We really should write that as -78.4 J foot-pounds. And there's the answer. Negative about the y, if this is the y, negative would be the opposite of the positive. This would be positive direction from right-hand rule. Therefore, the negative direction is going to be this. And that's what we want, because that makes sense, because that force is trying to rotate that hood up along that axis, and that's the negative direction. So that negative in the answer makes sense. Now, we could find what's happening about the x and the z, but the hood does not rotate about the x or the z. It is fixed to rotate about the y. All right, questions on that problem? So we just did a problem that talked about finding about the y-axis, or we could have the x-axis or z, and we adjust this ijk up top. But what if we want to know what's happening about a random line? What if we want to know about, I don't know, there's some point over here, and we have a new line right here. We want to know, well, how does it rotate about that line? Right? And we'll call it A prime or something. I don't know. If we want to know about a random line, we build the unit vector of that line. And how do we build the unit vector? Well, we take position vector over the magnitude between two known points. Meaning I would have to know 2 points on the line. Let's say that line goes through the origin and 2, 4, 0. We would build that unit vector as 2, 4, 0 on the top over the square root of 2 squared, 4 squared, 0 squared. 16, 20 square root of 20, so it's whatever over a square root of 20. When we get those ijk values, what we do with them is they will go right here then. Whatever those IJK values are, we would put them into the IJK at the top of the 3x3. And then when we solve it, it's going to give us the moment of that 24-pound force about that random line. Now, I'm only saying random because it's not on our drawing, and I'm not sure why I'd want to know that, because the hood only rotates about the y-axis here. But if I was curious about, well, what about this line of action or somewhere else, then I could find it by adjusting I, J, and K and building that unit vector. All right, questions on that? Now that really, talking about the specified axes, is really getting into the next section. I think it's section 5. And let me just introduce that while we're here. It doesn't say random in the book, but I'm going to put that there just so you know it's not about an axis. Axes. And this is known as the triple the triple scalar product. Triple scalar product is to find the moment about some other axes. Okay. And the triple scalar product, and again it says scalar. Scalar means I'll get a scalar answer when I have the moment. Let's try that again. When I have the moment about some line, and I put it in I, J, and K, and there's R, and here's F, Z, Y, X, Y, Z, X, Y, Z. This will be the unit vector of the line. Again, that's still a position vector, and this is still the force vector. That is the same as if I take the moment and dot it with the line of interest. The dot product usually gives us a scalar, right? It gives a scalar, and then we're dotting it with a cross product. So I'm really finding the line dotted with the cross product of the two forces. And when I write it in this form, when I put it in matrices form, it comes out like this. Okay, so I'm dotting the line with the cross product. So I'm really finding the moment and then telling me how the moment projects onto that line. And I can do it all in one shot. I can do that all in one shot. Now, what about the case if I have more than one force? The moment about that line is going to equal the sum of all the U dots R crossed F, or it equals the line dotted with all the R cross F's summed up. Meaning I can find all the moments about that line, then add them up. That's the first case. or I can find the moments, because this is really U dotted with the resultant moment. I can find all the moments and then dot it with that U. And either way is fine. All right, so let's do a problem about that. Again, I'm getting a little bit into the next class's lecture because there is, I think, 5 classes, but 4 weeks to get through. So I just want to get a little bit ahead since we didn't take that long and try to introduce more of that next section. So then we can double up a little bit next week also. And this is going to be similar to the car one, but we're going to actually do a problem where it is finding it. All right, let's see if I can get this working here. All right, didn't need super red. You know, I'm just going to draw it. It's a little ugly here. All right, here's our X, Y, and Z. I'm going to have a line here. Goes from A to A. It's from the origin. It goes through this point. And this point is going to be 4, 4, 0. And we'll make it meters. Obviously, there's the origin. And what it is I have up here, I have this random force at point A. Pick a better color. And the coordinates at point A are going to be, let's put it back there, -2, 3, 2. So that's the coordinates of A right there. Line of action shows it goes in all directions there. So all this, the coordinates will be pulled off the drawing. I'm just putting them in there so we have this. Now, if we took the moment about the origin, it would be this. We'd find ROA cross with that force. We've already done about a point. We've already done it about a point. Okay. If we wanted to do about the y-axis, so the moment about the y, we take from the y to point A, cross it with the F. And we'd have to use, one of these points, but we could use the same thing here because that goes from the y and it goes to point A. We would just take this then and dot it with the y-axis, which is a 0, 1, 0. So if we want to find the moment about this point, moment about this force, about the AA axis, we're going to take the unit vector of the AA, we're going to dot it with the R cross F. Okay. Now, for this position vector, it has to be from that line AA to the force. So we're going to have to go maybe from the origin to A right here. That's probably the easiest. We could use a point out here. We could go from A to big A. We could use that line. We could use anything in here. I'm thinking the origin one will be the cleaner one. So position vector from O to A. We take the A coordinate minus the O coordinate, -2, 3, 2 meters. If we want to find the magnitude or the unit vector of that, we would have to take that vector over its magnitude. We don't need that. What we're trying to build here is we want to put the unit vector of AA Here's a position vector. It goes from that line to the force. So we're going to put ROA. And then here is the force. Okay. So we can put ROA in here. That basically goes in here. So it's a -2, 3, and 2. The force vector we were given, I just didn't give it to you yet. It's a 30, 40, and a 20. So that is going to come down and go right in here. And what do we do about the AA? Well, we have to build that. We have to sort of build the unit vector of that. And the way we build that unit vector is the same we build any unit vector. We take position vector of it over R. Position vector for that's going to be from this point to this point. And this point is 4, 4, and this is origin. So that's going to be 4, 4, 0 on the top. Magnitude on the bottom is 4 squared plus 4 squared plus 0 squared. I'll just tell you what that's going to be. And since those are 45 degrees, sine and cosine of that basically give us 0.707i, 0.707j, and 0 in the k. Right? Because cosine of 45, I don't know if you recognize that, is that. So we're really just finding how much it goes there, how much it goes there, and how much vertical. So we put that now. This goes right down here. 0.707, 0. And if you go through that big mess, I'll give the answer here. Since it's a triple scalar product, when we do this U dot with the cross product, we get a number, we get a magnitude. This comes out to be 56.6 Newton meters. $56.6. Now, it looks as if that force should be pulling that way. But based on our answer, 56.6 is a positive number. So this force line of action must go underneath that AA axis to give us rotation that way, because that's the plus direction. Okay? That gets our answer. But to take it a step further, what's the moment vector in Cartesian vector form? Well, moment or any vector equals the magnitude times its unit vector. So if we take this, that's the magnitude, and multiply it by the unit vector, which is, where's the unit vector? Is this, right? That's for that line, and put that in there. Yo, come on, stop. We'll get 40i plus 40j plus 0k Newton meters. That gets us our moment as a vector. The triple scalar product here is going to give us the magnitude. So I really should get rid of this right there. Right? That one's correct, but this one isn't. That's the triple scalar product. It's the Templestone pilots. All right, questions about that? All right, moving forward, we are going to go next into the idea of a moment of a couple or moment of a force couple. That implies two forces working together. If I try to open a doorknob, I basically grab it with my hand and I rotate it if I'm trying to open, right? If I had a bigger, I had to open, maybe I'm in a ship and I have to open up the water main or something like that, or something big in an industrial place, or your steering wheel. If you go at 9 and 3, as they say, here's 9, here's 3, and I want to turn left, I would right hand grab there and turn this way, and left hand turn this way, and the result would, I would get it to rotate. This is known as a couple here when I have two forces. Sorry for that big marker. Two forces that are equal, but they are in opposite directions. So they're equal in magnitude, opposite directions. If I sum forces, it equals 0, so they cancel. So there's no translation of that steering wheel. There's only rotation, or a moment set up in our case, since we're talking about statics. So we're going to talk about moment of a force couple. That's also known as a couple moment. Or just a couple. And that's where we're going moving forward. And we'll pick up with that next week. All right, so questions of what I've covered here. Thank you, Jaden. All good? All right, so if everyone's good, or as you get good, you're free to take off. Otherwise, I'll hang out for a minute until everybody drops, and then we'll pick up next time. Have a great day. It's supposed to be really warm here if you're on the northeast coast of Pennsylvania. And enjoy the day.